Since this is a differential equations course, we're going to try and turn this continuous compound interest problem into an ordinary differential equation. But in addition to the continuous compound interest, we're going to have the interest on the account, but with deposits that are going on at the same time. All right, so let's look at the setup for that problem. So we have time t in years. We have an interest rate r per year. We have this s for savings account at time t and the bank account at time t. S at time 0 years is equal to S sub 0, S naught. And we're going to have K amount deposited into the account per year. Then we're going to compound n times per year. All right, let's start with the simplest case here. So the simplest case is n equals 1. And in that case, we're going to have S at time 0 is equal to S naught. Then we're going to have S at 1 year is equal to, well, it's S naught times 1 plus, since it's compounded once per year, it's r over 1, so just r. And at the end of the year, you're also going to you're going to add in this amount k that you deposited. Right, so that's kind of the simplest case we could do. It's not very realistic though, right? Normally people put in deposit money into the account more often than once per year. A more common thing to do is deposit a certain amount into the savings account every month. Let's go ahead and look at that one. So we have n equals 12. Then similar setup here, we're going to have s at time 0 is equal to s0. And we're going to have s at time here, I'm going to do 1/12 after 1 month. That's equal to s at time 0, the previous month, times the interest on the amount, so 1 plus, it's going to be r over 12. Right, we're only doing 1 month, so it's not to the 12th power. Then it's plus k over 12. The reason k is over 12 is because if you deposit k amount per year and only 1 month has elapsed, then you're only going to deposit 1/12 of the amount you would deposit in a year after 1 month. Right? So a little more complicated, and unfortunately that amount of complication actually makes this a much more difficult thing to solve for. So if you do s of 2 over 12, that's going to be s of 1 over 12 times 1 plus r over 12 plus another k over 12. And now here's the problem. In the last time, when we substituted the previous s over 12 into here, we ended up just getting powers of 1 plus r over 12, right, every time we did another month. The problem is, though, we have this k over 12 hanging around now. It is possible to simplify, but we're not going to do that. We're going to try and convert this into an ODE instead. All right, so there's a little trick for the ODE. So we're going to do something a little different. We're going to define delta t is equal to 1 over n. So it's kind of the length of one interval to compound. All right, let me just separate this here. So if we do that, we're going to have s, and it's going to be s of 1/12 here, so I'll have like s of 1 over n after the first compounding. And that's the same thing as s of delta t, right? That's going to equal, well, then we're going to have s at time 0, like we had before. We're going to multiply that by 1 plus, here it was r over n, so it's like r times 1 over n. So instead we're going to have r times delta t. So delta t times r. Then plus, here we had k times 1 over n, so now it's k times delta t. So we have delta t k. All right, so this is looking a little closer to a differential equation. So we've got s of delta t equals s of 0, and then we got 1 plus delta t times r plus delta t times k. Now we're going to change it just a little bit. So really what we did in this s of delta t and s of 0, that was the same thing as s of 0 plus delta t, right? Same thing, that we got that 0 from there. So we're going to write an equation where we have s at time t plus delta t is equal to s at time t, then we have this whole thing again, times 1 plus delta t times r plus delta t times k. Right, so we have some amount in the bank account at time t. We want to figure out how much is in there after a delta t amount of time, kind of one compounding, and we can figure that out by taking the amount we currently, previously had times the interest rate plus how much was deposited. So this kind of happens all at once to turn this into a differential equation. But what we're going to do is we're going to multiply this out a little bit, so we get s of t times the 1. Then we have s of t times delta t times r, and we have plus delta t times k. I'm going to subtract the s of t to the other side, and I'm going to divide everything by delta t. So we're going to end up with s of t plus delta t minus s of t. Then write divide by delta t everywhere. So we're going to get over delta t. Let me fix that delta. The deltas on this side all got divided out, so this is really just s of t, and I'm going to write r times s of t plus k. Now, if we let the limit go to, delta t goes to 0 in that limit, this is actually the derivative of this function s of t with respect to t. And on that side, I'll write over here limit as delta t goes to 0, are we going to get the derivative of ds dt here. The other side, delta t went to 0. There were no delta t's here, so this turns into r times s plus k. So this is actually the ordinary differential equation that we get if we have an infinite number of compound interest, and we're putting in kind of a very, very small amount of stuff continuously all the time, that at the end of the year it will sum to amount k. So this is the differential equation, and we're going to do some examples where we solve it.